We're live. Live, ladies and gentlemen. And today we're going to talk to whew, and today we're going to talk about attention from the small training playbook. And yes, it's a huge chapter about architecture and architectural choices. Um, and I decided that we need to slice it in very, very fine slices because I think there is a lot to cover in each one of them. And let's start with the attention. So attention, um, I guess everybody knows what attention is. So I'm not going to dive deep into like the basics, the foundations of like vanilla attention, but we will roughly in this like talk, we'll roughly go over a few claims about computational efficiency and like what dominates what feed forward layers, so attention during training and during inference, and then we'll dissect the most popular techniques, approaches to efficient attention. So, the first claim that the chapter starts with is that while feed-forward layers dominate compute during pre-training, attention becomes the main bottleneck at inference, especially with long contexts, uh, where it drives the compute costs and etc. etc. But basically, the authors claim that FFN layers dominate compute during pre-training, and that's where I first like questions the statement. Like, I mean, I don't have questions for it. I don't question the validity of the statement. It's just like I wanted to make sure and see how it plays out in the numbers. So I went a bit forward and um dig a bit deeper into what it really means. And thanks to Claude, I came up with two magical tables. First one is for training, and we'll see that for the FFN layers, we have 16, which is, well, I think we can dissect this constant into, well, probably we have two projections, right? Up projection, down projection. Um, and then we have in vanilla transformer, the hidden dimension of the FFN layer is 4 multiplied by d, right? So I guess if we do 4 multiplied by d, and it's up and down projection, that gives us, well, and it's d squared. So it gives us exactly 16. So, well, there we go. We have 16 multiplied by L, which is our context length, multiplied by d squared, because it's once again up and down projection. So this term, uh, compute-wise and memory-wise, is defined like dominated by d squared. Um, but in terms of flops, we have this L term multiplied as well. For attention, we have a similar picture for attention projections, but we have a very different picture for attention scores. For attention scores, as you might remember, we have this like huge attention metric matrix where we kind of see how each token attend to each one of the each other token, right? So it's like if we have L tokens, our context length, then the matrix is going to be L by L. And this is exactly what we see here in the table, that it's L squared multiplied by D. Um, and we can see that in like per layer total number of flops compared to bytes moved, like transferred from memory and in and out, we can see that the flops, they're bigger because they like the first term is multiplied by L and the second term is multiplied by L as well, which makes it L squared. So we can see that during training, uh, like we have compute bound process during training overall, but specifically to like specific to feed forward layers and attention scores, if our L is sufficiently small, and during training we'll see like how that plays out, but it is going to be most of the time sufficiently small. We can claim that FFN with the constant and with d squared is going to dominate the compute for the attention score here. So like it's basically a trade-off where the d squared, like L squared surpasses d squared term. And we can also, well, we can also claim that the computation for the attention projections should be counted in. And it kind of is accounted for, but nevertheless, there is like this point of change where the attention scores start dominating and where this L squared term starts dominating. And I decode, and I'd like to highlight that decode here is counted as if we have a valid KV cache. Um, the picture is different. So for the decode step, um, we need to calculate new data only for one new token. Um, and that means that we do FFN only for one new token, attention projections for only one new token, but the attention over the KV cache has this L term, still has this L term. So during decode, we have effectively memory bound process, which is dominated by the attention over KV cache. And well, since we already um, started on this like L context length change point, it's worth to highlight that usually the pre-training comes in three stages in terms of context length. We have bulk pre-training done at short L, which means that the attention scores still do not dominate the FFN layer. Then we have long context extension phase, where indeed, L starts dominating. And then we have SFT, RLHF stages on long context as well, where the picture is still like it's the same picture where attention dominates over FFN. But I think that when authors claim that FFN layers dominate compute during pre-training, what they meant really was that FFN layers dominate specifically during this bulk pre-training at short L. And this claim is supported by a few technical reports. We have Llama 3 that does bulk pre-training at 8K and then goes to 128K. We have Quen 2.5, which starts with 4K and goes to 32K, and Quen 2.5 Turbo, which goes through four different stages: 32K, 64K, 128K, and 256K. And I believe that they start with 32K because it's kind of continuous pre-training over Quen 2.5 base ish. I don't really remember. Quen 3, it goes from 4K to, well, they don't disclose the context length. I think it's probably the same context length, but they call it knowledge intensive data with STAM encodings, like very, very high quality data. And then they extend the training phase to 32K context length. DeepSeek V3 goes from 4K to 32K and then to 128K. Yes. And finally, that's the model I'm first hearing about is We, and it goes from 4K to 200K. I don't think they make this jump instantaneously. We probably have to read uh, the technical report in more detail. But the interesting find from the summary of this report is that only 1-2 billion tokens was enough for them to achieve a plateau in the loss once they extended the context length from 4K to 200K. Nice. So let's start with the vanilla thing. Like now to the attention techniques themselves. Vanilla thing is multi-head attention. Classical stuff. We have values, we have keys, and we have queries, and we do matmuls with them, and voila, we have our attention. And if we try to calculate the size of the KV cache, the equation goes roughly like this. It's 2 by n bytes y2. Oh, I think it's because it's K matrix and it's V, right? So it's two matrices, each one of the matrices. Um, yeah, it's n bytes by sequence length, by number of layers, number of heads, and dimension of the heads. So in the book, they did calculations for small llama and big llama, and it was for 8K context length. Uh, for big llama, it was 20 gigabyte of KV cache for a single query. Uh, and I took a liberty of extending calculating the size of the KV cache for 1 million context length. And for 70 billion model, it was 2.5, 2.6 terabytes, which is, it's a lot if we want to support 1 million context length for our paying customers. I'd say that it's probably unfeasible. So, well, you can clearly see the problem. We have, if we want to support long context, uh, we have to do something about the KV cache size. And there are various techniques on how on what we can do. Like um, you can go beyond what's described like in this talk. You can go I think it's called window retention, and I probably should have covered this. Maybe we should have another talk about it. Maybe at the end of this. Um, at the end of this chapter, I'm not sure. But like, I just realized that like, while we're going to talk about all four of the attention patterns methods presented in the book, we're kind of missed on other efficiency techniques that can be applied to make attention scale better and make attention work for long contexts. Um, Let me ponder it, and maybe we'll squeeze in another talk, maybe next week to go beyond what's described here. Um, Maybe not. Well, while we have you guys on the call, do you guys? Oh, let's first finish this talk, and then we'll discuss. So, the gist of it is that beyond multi-head attention, we have multi-query attention, grouped query attention, and multi-head latent attention. So, multi-query attention, the idea is simple: is that, well, instead of having different KNV matrices, what what if we share them across all of the heads? So all of the heads would have the same KV matrices. Well, it works. I will see the test results soon enough. It works fairly well, but the quality degrades. So a natural kind of middle ground between multi-query attention and multi-head attention is group query attention when we try to share KV matrices uh, between multiple queries, but not all of the queries. Um, well, it works better, and like you can find a solid middle ground. And at last, we'll talk about multi-head latent attention, which is not covered in depth in this book, and I took a liberty of going a bit beyond the book to figure out what that is. But the idea is that it's kind of multi-query attention in a sense, where we have the same learned KV matrix. But then in multi-query attention, we naively use the same KV matrix across all of the queries. But what if we um, use this KV matrices not directly? What if we use them to create the projections, like a low dimensional projections um, of the of the hidden state, right? And then when we need to calculate the actual attention scores, we do the up projection from the low dimensional space uh, and basically kind of reconstruct a low rank approximation of the KV matrices for each one of the heads. And each one of the heads is going to have its own low dimensional, well, low rank um, up projection. So it's kind of like degrading the quality of each one of the KV matrices, but having them separate instead of sharing them, in a sense. We'll dig deep into this like in the next few slides. So what happens here is that, well, we have step one, we have down projection. Well, we down project hidden state into this KV latent. So we have this learned shared matrix that is shared across all of the heads. And once we have a hidden state, we use this shared matrix to learn a single vector, this KV latent. That's the kind of result that we're going to store in our KV cache. Step two is that we define per head K and V up projections that can be applied to this guy. So first, we kind of uniformly transform hidden like vectors into latent hidden state vectors into some KV cache vector. And then we use individual matrices for each one of the heads to reconstruct K KV matrices per head from this shared vector. Then we down project hidden state into the query latent. So we have another matrix that shared matrix that projects the query, and then we have the up projection once again per head. And then finally, the trick here, like there's a nice trick about transposing and combining matrices together. So when we calculate the score, we have this query and well, what they call what is what here. So like they have queries and yes, queries and keys, right? So they have queries and keys, and when we substitute queries and keys with the actual latents that we got from the down projection and matrices that we use for up projection for reconstruction, this low rank reconstruction, we can do the simple transpose trick to combine the matrices together, and as you can see, these matrices, they kind of, it's a stable matrix that's going to be universal at all times per head. So it's kind of a single matrix that we apply to our learned shared KV vector that sits in between our query latent, our KV stored latent, and it kind of joins them together into the final score. At least that's how I read it. And Gemini was kind enough to give me a visual of what's happening there. So once again, we have shared stuff. So like our current hidden state produces cached latent and produces like using the shared matrices for like down projection to KV latent and down projection to query latent. And what's stored in KV cache is this, like what really matters here is that the thing that is being stored in KV cache is only this shared cached latent. So only a single vector stored for all of the heads. And that in terms of math, that drastically simplifies, well, brings the required memory down. And I think that this constant of 4.5, it's an arbitrary constant, right? Because we can probably play with the sizes of the down projection. Well, not with the down projection. Well, actually, yes. I mean, like, we can. I'll probably need to dig a bit deeper into multi-head latent attention, but I have a feeling that there is a hyperparameter of like how much do we compress the latent. But nevertheless, even if I'm wrong, uh, even if I'm slightly fuzzy about the nuances of how this kind of low rank decomposition works. Nevertheless, you can see here that instead of having uh, instead of being required to account for the number of heads and with a multi-head attention, classical multi-head attention, we have a single constant that's been reused across all of the heads. And when we have a sufficiently large number of heads, like it definitely makes the math easy and brings the number down. Um, and in the book, they ran a few ablations to see how these various types of attention perform. So we have uh, multi-head multi-head attention, the classical stuff. We have multi-query attention and grouped query attention. They didn't play with multi-head latent attention because they say that Nanotron that they used didn't support it back then. The, the, it might be different these days, but um, they didn't ablate multi-head latent attention. Uh, and another thing worth noting is that when we go from multi-head attention to grouped query attention or multi-query attention, the number of parameters goes down. So you can see here that in order to make the number of parameters comparable, they had to reduce the number of layers in case of multi-head attention compared to multi-query attention or group query attention. So when they ablate something, they don't use the same architecture to the point. So it's not the same number of layers. What they care about is the same number of parameters. And it's probably the right metric, but just something to be aware of that the depth of the models is different. And here are the results. So we have, well, pretty loss curves that are barely distinguishable from this, from the current zoom ratio. But we can see that multi-query attention performs worse and multi-head attention performs sufficiently, well, comparable with grouped query attention. And I zoomed in, so this is what we have at the tail of the loss curve. We have multi-query attention performing worst of all. Then we have grouped query attention with 16 groups, surprisingly. I'm not sure like why. It's like my gut would tell me that if we increase the number of groups, loss should go down, but it doesn't. So like I don't know why. It is the way it is. Maybe actually yeah, let's okay. It's the same number of layers, so I'm puzzled. I'm puzzled. I don't know why. Uh oh, actually ratios. Oh, I see. So I think that when they say group query attention ratio 16, it means that they have only actually two groups. So it's like the division factor. So they divide 32 by 16. Now it makes sense. So basically, GQA 16 groups means that we have only. I think it's just kind of confusing annotation. So it's actually two groups. It's like it's two groups. Each one of them has 16 heads combined. And now it makes much more sense. And I think it's that because I think that way because if number of like this ratio 16 meant that we have 16 shared query key and value shared matrices, then the parameter count would go up. And we can see that if the ratio count goes down, then parameter count goes up, and they even have to reduce layers, which now makes much more sense. So it's not 16 groups. it's this 16 ratio factor. So the smaller, the better. Um, and they didn't only count, like, they didn't only look at the loss, they also looked at the real world benchmarks, and we can see that multi-query attention, where they share a single KV matrices, it performs the worst. However, we have this weird phenomena for the open book QA where multi-query attention performs the best. Also, Wino Grandi, whatever that is, also shows some um, weird behavior where multi-query attention behaves differently, and we can see a lot of noise in these benchmarks, right? So it's aggregates across multiple runs, and we can see a lot of noise in these benchmarks. In the benchmarks where we have a much less noise, we have consistent behavior where multi-query attention and well, there is orange line here, right? So and also group query attention with high ratio performs worse. And at last, we need to talk about document masking. Here's another problem that we face when we try to train on real world data. Surprise, surprise, real world data is not uniform in a sense that the length of each one of the documents, each one of the files, each one of the sequences that we want to learn is different. So we can have 4 files, 4 sequences of different length. How do we train on them if we want to train using 4K sequences? One idea is that we can pad each one of the files up to 4K sequences, but that's going to be very wasteful. So another idea is that we can combine the files together until they reach the our required window and then continue. But then, if we do this naively, then file 2 would attend to file 1, and file 3 would attend to file 1. So we would kind of um, involuntarily embed the um, false knowledge that file 1 always comes before file 3 into the model. False bias. And if we take a look at the distribution of the length of the documents in various datasets, here it's FineWeb Edu, DCLM, whatever that is, FineMath, and Python Edu. We can see that most of the documents, they reside in this, well, below 2K length, which means that we have to somehow join them if we want to make training efficient. And here comes a neat idea. What if we play with our attention masking? So like in regular causal masking, we just like mask all the future tokens, right? So like we don't see into the future. But we can go beyond that. If we have tokens from different documents, we can alter the mask to make attention attend to make tokens attend to only to the documents, only to the tokens inside of that document. So this is like a good visualization of what happens here. And the authors, they measured how it performs compared to random shuffling the document, compared to joining documents together without this, like what's that called again? Intra-document masking, but joining documents together of the same roughly that belong roughly to the same category, roughly to the same group, using BM25 algorithm. And they compare it with this intradoc masking. And what they see is that validation perplexity. First, well, we can see that when the context window goes larger, validation perplexity goes up, which is counterintuitive. And to remind you what validation perplexity is, it's a measure of surprise when the model needs to predict the next token given some context for the held out text corpus, which means that we train on some part of the data, and when we validate on another part of the data, we measure the surprise that the model we measure the surprise that the model learned and that the model exhibits when we're trying to kind of feed this validation text corpora into the model. And it's kind of counterintuitive that when the context window goes larger, this perplexity goes up as well. Because when we have longer and longer context, it means that our probabilities, I mean, like the distribution should be narrow and narrow and narrower because it's conditional distribution, right? So it should monotonically go down. It can't really go up because like each one step it narrows uh, our window of possibilities. And I talked to Claude about it, and he gave me a few ideas about why that might happen. So even with Introdoc, we see like when they compare this random shuffling with BM25 with Introdoc, Introdoc shows uh like what's the opposite of steep? Flatter, let's call it like a flatter curve, but the perplexity still goes up. And Claude hypothesizes that it's because of the positional encodings. Uh because when we even if we mask properly the tokens properly, we still have positional encodings already embedded there. So we don't really account for uh, positional encodings, uh, and we don't shift positional encodings based on where the document starts. And that might explain, at least be one of the reasons why perplexity goes up. Um, and I guess it's kind of partially supported by this chart here that when validation perplexity when we measure validation perplexity of the models without positional encodings, uh, then we can see that this validational perplexity. No, I'm not sure. No, actually, let's take a close look at what we are reading here. So, with when training with the number of tokens that we trained on, we can see that validation perplexity goes down for all sequence length, which makes sense. And we can also see that for sequence length, well, they measure only on short sequences, so I'm not sure. Um, well, based on this chart, probably we should we should see uh, if the problem was not with the positional encodings, then probably the curve for um, well, actually, no, it's still all right. Now we can see that the curve for the smallest context length has the smallest perplexity across the entire training process, right? So this red line. And then the curve for the longest context has the highest perplexity, which corresponds to this chart as well, uh, which means that positional encodings are not the only ones, is not the only factor that affects rising perplexity, because otherwise, probably, we would see that perplexity of the longer contexts would be lower than perplexity of the shorter contexts, I think. Let me know if you guys think differently. Um, so yeah, we have this kind of mystery-ish thing, which was not, in my view, clearly explained in the book, like why this perplexity goes up. So we can only hypothesize, and I'd say it's probably positional encodings, but this chart shows that it's not only positional encodings, it's something else as well. And when it comes to real world, we know that Meta trained Llama 3 with intra-document masking. They found limited impact during short context pre-training, but significant benefits for long context extension. And the guys from Hugging Face, they ablated it. So they ran pre-training on short context with document masking and without document masking, and they didn't see any meaningful differences. But and like in real world benchmarks, well, we can see some differences, but we already saw that on this Vino Grandi benchmark. Multi-query attention beat everything, so hard to trust. All other more reliable benchmarks, they don't show meaningful difference. And this is like last slide, but they also mentioned in the book that they saw the difference on at long contexts. So, well, I think this is roughly it. We're done here. We have kind of like an unexplained phenomena here. So, like, this is probably homework for all of us to ponder, like, what it could be. And do we have any questions?
No, not right now.
All right, let me stop the recording then.